Welcome to Connected Components of Chaos. As a computer science major, data storage and retrieval, it's a big deal, right?
Absolutely. I mean, think about it from those student databases to social networks you're always using, even compilers.
Right, exactly. And speed is everything, especially when you're dealing with these massive data sets.
Yeah, that's where hashing comes in. It's like our secret weapon.
So let's dive into that. But before we get into these hash tables, I think it's helpful to start with something a bit simpler.
Yeah, like direct addressing, a good foundation.
So imagine you have this small set of student records, each with a unique ID. Let's say a 4-digit student ID. You could just create an array with a slot for each possible ID.
Yeah, so you're storing the records directly. It's direct addressing, pretty straightforward for these smaller data sets.
Exactly. But what happens when you start dealing with a huge number of potential keys?
Like all those possible 9-digit social security numbers.
Or think about like every possible variable name that a programmer could ever come up with.
You'd need this ridiculously massive array.
Right, it'd be like building a stadium to hold, a handful of people.
It's just not practical, and that's where these hash tables come in.
So instead of using the key directly as the index, you're using a hash function.
Right, so this function takes the key and maps it to a smaller table. Basically crunches it down to a smaller number that fits in the table.
Okay, so I see how elegant that is, but I'm already seeing like a potential issue here. What if two different keys map to the same slot?
Ah, that's a collision.
Yeah, and it sounds like it could lead to chaos.
Well, it's inevitable, when you're mapping this potentially infinite set of keys to a finite table, but don't worry, we've got strategies
Okay.
to handle these collisions, and the two main approaches are chaining and open addressing.
Okay, so we have these collision resolution strategies,
Yeah.
chaining, I'm picturing it like organized chaos.
It's a good way to think about it. Imagine each slot in the hash table is like a hook, right? If multiple keys hash to that same slot, we just create a linked list at that slot and add each colliding key to the list.
So it's like having these neat little queues forming at each slot, keeping things tidy even when there's like multiple keys that want to occupy the same space. What about searching for a key or even deleting a key?
Yeah, so with chaining, searching becomes a two-step process. You hash the key to find the right slot, and then you go down that linked list at that slot until you find your target.
Okay,
And deleting is just as straightforward. You just remove the element from the linked list.
I see.
So it's pretty clean.
Yeah, chaining has a certain elegance to it, but
Mm.
open addressing, now that sounds a bit more adventurous.
Yeah, with open addressing, we get a bit more persistent. So instead of using these linked lists, we store all the elements directly in the hash table.
Okay.
And if a slot's already occupied, we don't just give up. We probe the table.
Oh, okay.
We search for the next available empty slot.
So it's like playing a strategic game of musical chairs, kind of, with our keys.
Yeah, that's a fun way to think about it. And how we probe the table can vary. The simplest method is linear probing, where we just move to the next slot step by step until we find an empty one.
Okay, so that sounds simple enough, but wouldn't that lead to like bunching up, like rush hour traffic jams in certain areas of the table?
Exactly. That's called primary clustering.
Oh,
If lots of keys hash to nearby slots, they tend to probe the same sequence, creating these long chains of occupied entries. To address this, we have other probing methods, like quadratic probing, which uses a quadratic function to kind of determine that step size.
okay, so you're spreading things out a bit more, so we're getting a little bit more strategic with our musical chairs game. Is there a way to make probing even more sophisticated?
Yeah, absolutely. The most effective approach is what's called double hashing,
Okay.
where we use a secondary hash function to actually determine that step size. So it makes the probe sequence more random and reduces that clustering even further.
I see, double hashing, pretty clever. But I'm curious, what happens when you need to delete a key with open addressing? Wouldn't just removing it create gaps in the probe sequence and then mess things up for future searches?
You're absolutely right. Deleting in open addressing, it is a bit tricky. You can't just remove the key and mark the slot as empty because it might break that probe sequence for other keys. So what we do is we mark the slot as deleted, meaning it's no longer empty, but it doesn't contain the original key. This way, we're keeping that probe sequence intact.
So it's like leaving a breadcrumb trail
Exactly.
to make sure that others can still find their way. But I guess this means that search times could still be affected by deleted entries, even if they're not actually there.
That's a good point, yeah. Search times in open addressing can be affected by, the number of elements that were ever in the table, even after deletion. That's a trade-off to think about compared to chaining.
Right.
which handles those deletions a little bit more gracefully.
Just this balancing act, right?
It is.
Chaining might use a bit more memory, but it handles deletions gracefully. Open addressing is maybe more memory efficient,
Yeah,
but those dilutions can leave a bit of a messy trail.
exactly. Now let's get to the heart of a hash table, the hash function itself.
All right, so we've talked about how a hash function maps keys to slots, but what defines a good one? What qualities should we be aiming for?
Well, it all comes down to speed. A good hash function should be fast. It should distribute the keys uniformly across the table, and it should also avoid patterns.
Okay,
We don't want it to slow down those lookups, and we want to minimize collisions, especially with open addressing.
makes sense. Speed and even distribution, it's all about efficiency. Are there specific techniques or strategies for designing these hash functions?
Absolutely. One classic method is what's called the division method, where you divide the key by the table size and you use the remainder as the index.
Ah, so you're essentially squeezing those big keys into a smaller range using the modulo.
Precisely. It's simple, and it works pretty well if you choose a suitable table size, preferably a prime number, just to help with that even distribution.
Prime numbers, always coming to the rescue. But what about other methods? Are there any alternatives to division?
Yeah, another common method is called the multiplication method.
Okay.
This is where you multiply the key by a constant. That constant's between 0 and 1. You take the fractional part of the product, multiply that by the table size, and then you just use the floor of that result as your index.
Okay, that's a bit more involved. Why would we choose multiplication over division?
It offers a bit more flexibility when you're choosing that table size, and certain constants, like the golden ratio, work exceptionally well with this method.
Golden ratio now we're talking. But can we always assume our keys will be perfectly randomly distributed?
That's the catch, isn't it? Real-world data, it often has patterns, right? And that can actually lead to more collisions. That's where the concept of universal hashing comes in.
Universal hashing. Sounds powerful. Does that mean there's some magical constant that works for all possible keys?
Not quite a single constant, but rather a universal class of hash functions.
Interesting.
We randomly choose a hash function from this class at the beginning of our program's execution.
So we're choosing a champion from this league of excellent hash functions. But how does this help with those patterns in the keys?
Think of it as a defensive strategy. Even if someone tries to choose keys that collide with a specific hash function, they won't know which one we've selected from our universal class.
Okay.
It's all about making the hash table more robust against potentially malicious or biased data.
So we're adding a layer of randomness, a bit of mystery, to outsmart those who might try to exploit those weaknesses in our hash table. I like it.
Mm.
But how do we know if a class of hash functions is truly universal? What guarantees does it offer?
So a universal class of hash functions guarantees that no matter which keys are chosen, the probability of two distinct keys colliding is less than or equal to 1 divided by the table size, even in the worst case scenario.
So it's like having that safety net,
Exactly.
making sure those collisions are kept in check, no matter how tricky that data gets.
Exactly. And it's important to note there are different levels of this guarantee.
Okay.
You know, we have the universal hashing assumption, which considers all possible key pairs. Then you have the simple uniform hashing assumption, which only considers a single randomly chosen key and its collision probability with all the other keys.
So different levels of robustness depending on how strict our requirements are. This is getting really fascinating. We've covered so much already. From simple, direct addressing to these more complex collision resolution strategies. And now we're venturing into the world of universal hashing.
It's a whole universe.
It is. It feels like we're just scratching the surface here. What's next on our hashing adventure?
Now that we've got those fundamental building blocks of hash tables down, let's talk about how we can make them even more powerful and adaptable. Remember when we touched on the load factor?
Yeah, that's like a measure of how full our hash table is getting, right?
Yeah.
We want to keep it kind of low to avoid those collisions and keep those searches super fast.
Exactly. But what if we don't know in advance how many elements we're going to have? Like, what if our data set is always changing, growing, shrinking? That's where adaptive hashing comes in.
Oh, okay.
Imagine a hash table that can actually resize itself on the fly,
Whoa.
dynamically adapting to the amount of data it needs to store.
A self-resizing hash table? That sounds incredible. How does that even work?
It's surprisingly elegant. We start with a reasonable table size and just keep an eye on that load factor. If it starts to get too high, meaning our table's getting crowded, collisions are more likely, we just double the size of the table.
Okay, so we create a bigger table and move everything over. Sounds like a lot of work.
It sounds like a heavy lift, but the beauty is when we double the table size, we rehash all the existing elements.
Okay.
And it turns out to be super efficient when you look at it over a sequence of operations.
How does doubling the table size save us time in the long run?
Think of it this way. As the table grows, those rehashing operations, they happen less and less often. It's like spreading out the cost of moving to a bigger house over time. We use a technique called amortized analysis to show that even with those occasional rehashing bursts, the average cost per insertion actually stays pretty constant over a long sequence of operations.
So it's like finding that balance, right? Keeping the load factor in check without constantly resizing the table. It's a balancing act.
Yeah.
But what happens if our data starts shrinking? Do we just have this extra space?
That's where the adaptability comes in. If that load factor gets too low, meaning we've got lots of empty slots and we're wasting memory, we can just have the table size and rehash everything. Adaptive hashing basically ensures that we're always using our memory efficiently, whether the data is growing or shrinking.
Adaptive hashing, it's like this hash table that can anticipate its own needs. It's pretty amazing. It feels like we've uncovered a whole new dimension to these hash tables.
We've definitely gotten into the core mechanics and some cool optimization strategies. But there's even more to hashing. Like, did you know there's this fascinating connection between hashing and probability theory?
Oh, probability theory. Now you're taking me back to my math classes.
Well, remember how important it was to choose a good hash function to distribute those keys uniformly? Probability theory helps us analyze, the likelihood of collisions and understand how different choices for those hash functions can affect performance. It's like having this mathematical lens to predict behavior and optimize.
So it's not just about the algorithms, it's also about the underlying math that makes it all work.
Precisely. Probability theory gives us the tools to analyze how our hash table is going to perform on average, even when we don't know exactly how those keys are going to be distributed.
It's amazing how all these areas of computer science, algorithms, data structures, even math, all come together in this concept of hashing.
It's like this interconnected web of knowledge, right? And the applications go way beyond just dictionaries and data retrieval. Hashing is super important in cryptography, security, distributed systems. It's truly foundational in computer science.
It's incredible that something as simple as mapping keys to slots has such a wide impact. Before we wrap up, I've got one last question. Is there a perfect hash function out there? One that just eliminates collisions entirely?
The eternal quest for the perfect hash function.
It would be amazing.
It would be, wouldn't it? It really depends on what we mean by perfect.
Well, in a perfect world, it would be so clever that we wouldn't have any of those pesky collisions. Is that even possible?
It's a nice thought, but often it's just not achievable, especially when our data sets are dynamic and we don't know all the keys beforehand.
Okay, so no zero collisions. But what about a hash function that gives us the absolute most uniform distribution of keys, even with those weird patterns in the data?
Now, that's a more achievable goal. And universal hashing, with that random selection from a family of good functions, gets us pretty close.
Right.
But even with universal hashing, there are trade-offs.
Okay.
Some functions are really fast to compute. Some might give you slightly better distribution.
So it's finding that balance between speed, that uniformity, and how complex the function is to actually implement. It sounds like there's no one best hash function, but a whole bunch of options depending on what we need for our application.
Exactly. That's one of the things that makes hashing so interesting. It's this constant interplay between theory and practice. We have these frameworks to guide us, but we also need to make practical choices based on our data and how we need our systems to perform.
It's a mix of art and science, finding that sweet spot. Well, this has been a fascinating journey through the world of hashing. We started with direct addressing, explored adaptive hashing, and delved into these universal hash functions. What are your final thoughts for our listeners who are hopefully excited about hashing? I feel we've uncovered this whole world within hash tables. They're so versatile, so efficient.
They really are. It's like having that Swiss Army knife of data structures.
And for our listeners who are ready to jump in, what's your advice?
I think the best way to learn is to just dive in. Experiment with different hash functions. Try out chaining and open addressing. See what happens when you change that load factor.
Get your hands dirty with some code.
Exactly. There's nothing like hands-on experience to really understand what works best.
And that choice of hash function, it's so crucial.
It really is. It can make all the difference for efficiency.
So to wrap up, I'm curious, what's next for hashing? Any exciting new areas that people are exploring?
Always. Remember we talked about universal hashing as a way to protect against worst-case scenarios. But what if we could combine that robustness with the dynamic nature of adaptive hashing?
Whoa, so like a dynamic duo of hashing techniques.
Exactly. Imagine a hash table that could not only resize itself, but also switch between different universal hash functions as it goes.
So it's constantly evolving.
Yeah, adapting, outsmarting anyone who tries to predict it.
Like a super-powered hash table.
Hmm.
What would that look like in practice? What are the benefits?
Well, think about it. Even better distribution of keys, fewer collisions, and by switching functions constantly, it becomes incredibly hard to exploit those weaknesses.
So much more secure.
Absolutely.
It really opens up a whole new realm of possibilities for optimization and security. Makes you wonder what other innovations are out there just waiting to be discovered.
It really does. Even something as simple as mapping keys to slots, it just leads to all these incredible challenges and solutions.
Well, I think that's a perfect note to end on. We've come to the end of our deep dive into the world of hash tables. Thank you so much for taking us on this journey.
It's been my pleasure. Hopefully everyone listening has a new appreciation for this incredible data structure.
And remember, there are so many fascinating concepts in computer science waiting to be explored. Keep learning, keep experimenting. Who knows? Maybe you'll be the one to discover the next breakthrough in hashing.
Until next time, happy hashing.